The $2 liquid that replaces a $2,500 repair is a chemical-based catalytic converter restoration method that works by breaking down carbon deposits inside the exhaust system, improving exhaust flow, restoring engine efficiency, reducing emissions blockage, and often clearing check engine light conditions related to catalyst performance when the issue is caused by carbon buildup rather than structural failure. And this method is commonly available in hardware stores for under $2, while the entire process requires no mechanical tools, no garage lift, no dealership appointment, and no professional mechanic intervention. Only a controlled driving cycle where engine temperature rises, exhaust gases reach sustained operating heat, and chemical vapors circulate through the catalytic converter to dissolve carbon layers inside the honeycomb structure. In the automotive repair industry, catalytic converter replacement is one of the most expensive standard repairs, with professional service centers charging between $1,800 and $3,500 depending on vehicle type, emission standards, and part compatibility, while diagnostic testing alone often costs around $150 before any repair work begins, and independent repair shops still charge between $800 and $1,500 using aftermarket converters. Yet, despite these price variations, the most common diagnosis given to vehicle owners remains the same. The catalytic converter is clogged, damaged, or inefficient and must be replaced, with no alternative explanation or restoration method offered in most service environments. The catalytic converter itself was introduced in the mid-1970s as part of strict environmental regulations under the Clean Air Act of 1970, which forced automobile manufacturers to reduce harmful emissions from internal combustion engines. And by 1975, companies such as General Motors, Ford, and Chrysler had implemented catalytic converters into mass production vehicles. But early converter designs were highly sensitive to fuel quality and combustion efficiency, and under real-world driving conditions, they often became clogged with carbon deposits within relatively low mileage ranges, sometimes as early as 20,000 miles, especially in vehicles exposed to poor fuel combustion, short-distance driving, or engine tuning issues. To solve this early problem, factory engineers developed solvent-based cleaning procedures that were officially documented in technical service bulletins and repair manuals, which involved adding measured chemical additives into the fuel tank that would mix with gasoline, vaporize during combustion, and travel through the exhaust system at high temperature, allowing the chemical vapors to reach the catalytic converter, where they would interact with carbon deposits, gradually breaking them down and restoring exhaust flow without damaging the catalyst coating made of platinum, palladium, and rhodium. During the late 1970s and throughout the 1980s, these cleaning procedures were widely used in dealership maintenance schedules as part of routine servicing alongside oil changes, spark plug replacement, and fuel system maintenance, and independent mechanics across rural towns, agricultural regions, and industrial sectors also adopted similar methods because they were cost-effective and reliable for restoring engine performance in vehicles experiencing carbon-related exhaust restriction, particularly in diesel engines, tractors, buses, and long-haul trucks that operated under heavy load conditions. By the 1990s, however, the automotive repair industry began to change significantly as catalytic converter replacement evolved into one of the most profitable repair categories, eventually forming an estimated $18 billion annual industry in the United States alone, where the wholesale cost of a catalytic converter ranging from $80 to $250 could be marked up to retail prices between $1,200 and $3,500 installed, creating extremely high profit margins that exceeded 600% in many cases before labor costs were even added. Labor charges further increased total repair costs because catalytic converter replacement jobs, which typically required only 45 to 90 minutes of actual mechanical work on a lift, were billed as multi-hour procedures at hourly shop rates between $150 and $200, which allowed dealerships and service centers to generate invoices exceeding $2,500 for a single repair, turning what is mechanically a straightforward replacement into one of the most profitable standard services in automotive repair. As modern diagnostic systems evolved into OBD2 technology, error codes, such as P0420, which indicates catalyst efficiency below threshold, became the primary trigger for replacement recommendations. And in most repair shops, technicians rely on scan tools that immediately classify the catalytic converter as failed when oxygen sensor readings fall below acceptable limits, even though these readings can often be influenced by temporary carbon buildup, exhaust restriction, fuel mixture issues, or sensor contamination rather than permanent structural damage to the converter itself. Over time, industry training materials, repair manuals, and warranty policies gradually discouraged the use of solvent-based cleaning methods, often labeling them as unreliable, outdated, or potentially unsafe, while customers were increasingly asked whether aftermarket fuel additives had been used. And in some cases, such usage was interpreted as potential contamination that could void warranty coverage, reinforcing a system where chemical restoration methods were removed from standard repair protocols and replaced almost entirely by full replacement recommendations. Despite these changes, the internal structure of a catalytic converter has remained fundamentally the same since its invention, consisting of a ceramic or metallic honeycomb structure coated with precious metals like platinum, palladium, and rhodium, which act as catalysts to convert harmful exhaust gases, such as carbon monoxide, hydrocarbons, and nitrogen oxides, into less harmful compounds like carbon dioxide, nitrogen, and water vapor. But over time, carbon deposits from incomplete combustion, oil burning, rich fuel mixtures, and short-trip driving accumulate on the surface of the honeycomb, restricting exhaust flow without necessarily damaging the core structure. When oxygen sensors, placed downstream of the catalytic converter, detect reduced efficiency, they send voltage signals to the engine control module, which interprets this as catalytic failure and triggers a PU420 diagnostic code. But in many real-world cases, the converter is still physically intact and only suffers from carbon fouling, meaning the restriction is caused by buildup rather than structural breakdown, which creates a scenario where restoration is technically possible if the deposits can be chemically dissolved and thermally broken down. Hydrocarbon-based solvents introduced into the fuel system during a treatment cycle vaporize during combustion and travel through the exhaust system at temperatures between 800 and 1400 degrees Fahrenheit, entering the catalytic converter, where they interact with carbon deposits. And under sustained heat, these deposits soften, loosen, and break apart through a combination of chemical solvation and thermal decomposition, while the catalyst coating remains unaffected because its thermal tolerance exceeds 3000 degrees Fahrenheit, ensuring that only carbon buildup is targeted during the process. For effective results, the process requires specific conditions, including a low fuel level to increase solvent concentration, a fully warmed engine to ensure optimal combustion temperature, and sustained highway driving between 2500 and 3500 RPM for 30 to 45 minutes, which maintains continuous exhaust flow and heat long enough for the solvent vapors to circulate throughout the catalytic converter and act on carbon deposits across the entire honeycomb structure. After completing this driving cycle, diagnostic trouble codes are cleared using an OBD2 scanner, and the vehicle is monitored over the next several driving miles to confirm whether the check engine light returns, and in successful cases where carbon buildup was the primary issue, the system stabilizes and emissions performance improves as exhaust flow returns closer to factory specifications, demonstrating that the converter was restricted rather than permanently damaged. However, it is important to understand that this method does not work in all cases, because catalytic converters that have suffered physical damage, such as melted ceramic cores due to overheating, broken honeycomb structures caused by a mechanical impact, or chemical contamination from coolant leaks due to head gasket failure cannot be restored using solvent-based cleaning, since their internal structure is permanently compromised and requires full replacement. Real-world usage of this method has shown that a significant number of vehicles previously diagnosed with catalytic converter failure were actually suffering from carbon restriction rather than structural breakdown. And in these cases, chemical cleaning, combined with proper driving conditions, has successfully restored exhaust flow, reduced diagnostic error recurrence, and prevented unnecessary replacement costs, highlighting the importance of accurate diagnosis and understanding the difference between clogging and failure. Ultimately, the difference between a low-cost chemical restoration and an expensive catalytic converter replacement lies not in the technology itself, but in how the problem is interpreted. Because when carbon fouling is mistaken for physical failure, it leads to unnecessary replacement. But when correctly identified, it allows restoration of function at a fraction of the cost using methods that have existed since the earliest generations of emissions-controlled engine systems.